In this lecture, we conclude our study of Chapter 4 by looking at problem solving related to redox active species and oxidation reduction reactions. And our starting place for this is our oxidation number table. You should print this table out so you have it available to you when you're doing your ALEX homework problems and your recitation session problems and for your next exam and for the final exam. This will be a convenient table to have available for you. We're not going to go through all the individual rules as we've already covered those, but in this video we will apply these rules. So here's a series of 6 compounds, and we will assign oxidation numbers to each atom in each of the following compounds. The first compound is KiO4. You would name that potassium periodate. In this case, we would know that potassium is +1, oxygen is -2, and since we have 4 oxygens at -2, iodine must be +7. That may look slightly unusual to you as you think of iodine as a halide and you think of binary ionic compounds with iodine as -1. And indeed, that is commonly the case that occurs for iodine. But when it's in an oxoanion, it can be a positive charge, and the iodine here is a reactive species. This periodate is a good oxidizing agent. Next up, we have ionic compound iron 3 hydroxide, which right off tells us what one of the oxidation numbers is. But as we work our way through, we again have oxygen is -2, hydrogen is +1, and that makes sense because the hydroxide polyatomic ion has a net charge of -1. Having 3 of those hydroxides makes iron as a +3 oxidation number. Next up, we have hydrogen in a different type of environment. This is magnesium hydride, a compound that is proposed for use in hydrogen storage for hydrogen fuel cell systems. Magnesium is an alkaline earth metal. Being a metal, it's electropositive, and it's got a positive charge state on it, and it's +2. That makes the hydrogen -1 for each. Next up, we have NH4F, that is, compound is ammonium fluoride. NH4 you recognize as a polyatomic ion. Fluorine is always -1. Hydrogen is +1 in this case, making nitrogen a -3. Next, we have a covalent compound, carbon dioxide. Oxygen is -2, therefore carbon must be +4 to counterbalance that charge. And finally, we have an alkane, that is copper in a reduced state. Here we have hydrogen as +1, and 4 of them means that carbon must be -4. So we can see in the last two, carbon can vary anywhere from +4 to -4. And in fact, if we take methane and we burn it, it oxidizes and goes from -4 to +4. Following along that same idea, we're going to look at some types of redox reactions, and we covered 4 of them last time: combination, decomposition, displacement, and combustion. Let's look at 4 different reactions and see if we can classify them properly into one of these 4 classes. Here are our 4 reactions. The first one is one we just looked at, methane oxidation to go to CO2 plus water. That's a combustion reaction. Methane's the primary gas in natural gas, primary component, and releases a lot of energy when it oxidizes. Next up is the aluminum reaction with water to form aluminum hydroxide and hydrogen. This was part of the video that we saw earlier where we looked at the aluminum nanoparticles coming out into the moist Missouri air and igniting. It turns out that while aluminum does react with oxygen, it's the water that really initiates the reaction, and the hydrogen that's released created the fireball that you saw above the reaction. So this then is a displacement reaction because the aluminum is displacing the hydrogen in water. Next up, we have sodium elemental reacting with chlorine gas elemental to give sodium chloride, a compound. That's a combination. Lastly, we have NaClO3, that is sodium chlorate. If we heat this, it will decompose, releasing oxygen gas and forming sodium chloride. This is a decomposition reaction. Next, we'll look at balancing redox reactions. Before we start, there's an important note here. Chapter 4 uses the oxidation number method, and we don't suggest you spend effort on that. In the prior video that we looked at, we used the half reaction method, which is the preferred method or the better method and gives you the correct answer for all systems. And that is in chapter 21. So you should go to chapter 21 and study the first two sections and use the half reaction method for balancing redox reactions both in acidic and in basic media. We'll have more complex exam problems and they'll require you to use the half reaction method like we looked at in the prior video. And so we're going to use that method here to correctly solve or balance redox reactions. This is the general method that works for all systems. Quickly reviewing the rules for balancing redox reactions. We determine the oxidation numbers to decide which species are undergoing redox, and we divide the reactions into the species that's undergoing oxidation and the species that's undergoing reduction. Then we take those separate half reactions and balance the atoms and charges within each one. Once those are balanced, then we multiply each half reaction by an integer as necessary to make the electrons equal in both half reactions, so that when we then recombine the half reactions, the electrons will cancel. Finally, if the reaction is in basic media, we'll add hydroxide to both sides of the overall reaction as necessary to convert the protons into water, and leaving hydroxide as the excess species. Now we'll start off with a very simple case, and that is the reaction of copper-2 in water with zinc metal to produce copper-1 plus zinc-2. We've ignored all of the spectator ions. Those are not here. So we've eliminated those in this case. You'll see this when you get into General Chemistry 2. Oftentimes you'll actually have the reactive species physically separated, and they will transfer electrons through a cell, through what's called a electrochemical cell. And if you look at this reaction using the methods of chapter 3, you might say, well, okay, we have a copper on the reactant side, a copper on the product side, one zinc on the reactant side, one zinc on the product side. We're done. This looks like it's balanced, but it is not. If you carry out this reaction in an electrochemical cell, you'll find that the stoichiometry does not follow a one-to-one reaction. And there's a clue that this is not correct, that our one-to-one balancing is not correct, because our reactants have a net charge of +2, and our products have a net charge of +3. So to solve this, then we'll do our redox balancing, and let's identify the oxen red half reactions. Copper-2 going to copper-1 is the reduction half reaction, and zinc going to zinc-2 is the oxidation half reaction. Now we need to balance each of these with respect to charge, and so for the copper-2 going to copper-1, that's going to take 1 electron. And we'll see that the copper-2 plus 1 electron gives us a total of +1 charge on the reactant side, and we have +1 on the product side. Therefore, the charge is all balanced. That's nice and happy. Now, the next half reaction, zinc going to zinc-2, we have 0 charge on our product side. We need 0 on our reactant side. We need 0 on the product side, so we'll need to add 2 electrons to get there. Once we've done this, we see that the zinc reaction involves 2 electrons and the copper only involves 1. So we're going to need to multiply the copper half reaction by 2 so that the electrons will cancel when we combine them. And when we do that, then we end up with 2 copper 2s reacting with the zinc metal to give 2 copper 1s and a zinc 2 ion. Now the atoms are balanced and the charge is balanced. We start off with a total of +4 and we end up with a total of +4. This is the correct equation, and it also accurately describes the stoichiometry that we observe in our experiments. Next, let's take this redox reaction. We have a species Cr2O7 2-. This is a polyatomic ion. It's known as dichromate. Dichromate reacts with iodide to form chromium 3 ion plus iodine. We can assign oxidation numbers, and if we do this, we'll see that chromium in dichromate exists in the +6 state. Iodide is the -1, of course. Chromium 3 is +3, and molecular iodine is 0. This tells us that chromium is undergoing reduction from +6 to +3, and iodine is going from -1 to 0. So that's undergoing oxidation. So let's look at the first half reaction, the chromium half reaction. We have dichromate going to chromium 3, so we'll need to put a 2 in front of the chromium 3 to make the chromium atoms balance. We have 7 oxygens in dichromate, so we'll need 7 waters on the product side. That balances the oxygens. Next up, we'll need 14 protons on the reactant side to counterbalance the 14 hydrogen atoms on the product side in that reaction. Now, once we've done this, we can look and see what our total charge is. We have a total charge of +14 - 2. That's a net charge of +12 on the reactant side. And then on the product side, we have a total of +6. So we need to add electrons to this to turn the two sides to be equal, so we're going to have to add them onto the reactant side. We'll have to add 6 negatives to the reactant side to make that a total of +6. So then we'll end up with +6 on the reactant side and +6 on the product side. That's our net charge. And that also is consistent with the oxidation center change. The chromium is going from +6 to +3. That's a 3-electron process. There's 2 atoms that do it, so it's a total of 6 electrons. We need 6 electrons as reactants to get chromium from +6 to +3. Next, we'll look at the iodide to iodine half reaction. This is fairly straightforward. We have 2 atoms of iodine in iodine on the product side, so we need to put a 2 in front of the iodide. Therefore, that's a -2 charge, so we'll have to add 2 electrons to the product side to make both sides -2. Now, given this, we know that we've got a total of 6 electrons on the reactant side of the chromium and 2 electrons on the product side of the iodine, so we'll need to multiply the iodine reaction by 3 to make things balance out. So here's our 2 half reactions. We're going to need to multiply the second half reaction by 3 to get everything to balance out nicely. We see that here. Then we can add those 2 half reactions together. And now the 6 electrons on the reactant and product sides cancel. And we end up with the net reaction at the bottom. 14 protons plus the dichromate plus 6 iodides gives 2 chromium 3 ions, 3 molecular iodine, and 7 waters. That is all balanced with respect to atoms in charge. The next problem we're going to look at is in basic solution. We'll look at permanganate, MnO4- reacting with oxalate, that is C2O4 2-. 2 polyatomic ions are reacting. and they'll produce manganese dioxide, which is a brown precipitate, and the carbonate ion. This needs to be done in basic media. That's where the MnO2, which is correctly called manganese 4 oxide, it has a common name of manganese dioxide, but the IUPAC correct name is manganese 4 oxide. So the manganese dioxide or manganese 4 oxide is our product, and that exists only in basic media. In acidic media, it dissolves, and the reaction goes a little differently. So let's divide this into half reactions, and if we do this, we'll see that permanganate, MnO4 minus, goes to the manganese 4 oxide. So manganese is going from +7 to +4. And in the oxalate case, going to carbonate, we'll see that the carbon here has an oxidation number of +3, and it's going to a +4. So manganese is reduced, and the carbon is being oxidized. So the full process then for balancing the half reactions is as follows. First off, we have the permanganate going to the manganese 4 oxide. Those two manganese atoms are balanced. For the oxalate to go to carbonate, we need to stick a 2 in front of the carbonate. That's our first step. Now the carbons are balanced. Next, we need to balance the oxygen atoms by adding water. So for the permanganate half reaction, we need to add 2 water molecules. So now we have 4 oxygens on the reactant side, 4 oxygens on the product side. For the oxalate reaction, we have to add 2 waters on the reactant side so that our total number of oxygens is 6 on the reactant and 6 on the product side. Now we need to balance the hydrogen atoms by adding protons. We can do that, and for the first reaction, we have to add 4 protons to the reactant side. For the second one, we need to add 4 protons to the product side. That's just how it worked out, because each one has 2 water molecules. Finally, we need to balance the charges by adding electrons, and for our manganese reaction, we have to add 3 electrons because it needs to be a net charge of 0 on the reactant side. And then we have to add 2 electrons in the oxalate reaction on the left-hand side, or excuse me, on the right-hand side. We have to add the 2 electrons to the products to make a net of -2 for both reactants and products. Now, once we've done this, we've balanced the reactions with respect to atoms and with respect to charges. But we can't add the 2 reactions together because the manganese reaction has 3 electrons and oxalate has 2 electrons. So we'll multiply the manganese reaction by 2 and the oxalate reaction by 3. Now we'll have 6 electrons on both reactant and product side. And by multiplying the first one by 2, we see the resultant is here, 6 electrons plus 8 protons, plus 2 permanganates gives 2 manganese 4 oxides plus 4 waters. The second one we multiply by 3, and the resultant is, as shown, 6 waters, 3 oxalates to give 6 carbonates, 12 protons, and 6 electrons. If we add these 2 together, we'll see electrons will cancel from both sides. In fact, a bunch of the waters and a bunch of the protons cancel. And so the lines are drawn through everything that involves getting canceled. The 6 waters drop down to 2 waters. And then on the product side, the 12 protons drop down to 4 protons. So we have our resultant reaction, 2 permanganate plus 2 water plus 3 oxalates gives 2 manganese 4 oxides plus 6 carbonates plus 4 protons. But this reaction is in acidic media. And our first statement was we need to do this in basic media. So we're going to need to add 4 hydroxides to both sides, because 4 of the hydroxides on the product side will wipe out the 4 protons. And we do that, and then we cancel the excess water. So our first line, we've added 4 hydroxides to both sides. The second line, we've combined the protons and the hydroxides to form water. And the third line, we've canceled the excess 2 with the 2 waters on the reactant side with 2 of the waters on the product side, giving us our final balanced reaction in basic media. So it's a lot of steps, but it gets us the correct answer that properly describes the stoichiometry for this reaction. 2 permanganates plus 3 oxalates plus 4 hydroxides gives 2 manganese, 4 oxides plus 6 carbonates plus 2 waters. Now, the last thing that we're going to cover is reaction prediction. Remember back to our last video, we did some predicting on reactions, precipitation reactions. We mixed 2 electrolyte solutions and identified, do we get a precipitate or not? Then we took acid-base reactions and we said, okay, we'll mix these species together, do we get a reaction or not? Well, if we have acid and a base, we sure enough get water to produce. The last thing we're going to do is with redox. We're going to compare a couple of reactants, mix them together, and see, does a reaction occur or not? This activity series is another good table for you to print out. This is one that you, of course, would not commit to memory. Hopefully you would have some feel for the trends. The things at the bottom are the ones that will exist as metal, and the ones at the top will exist as ions. But if you print this out, you'll be able to use this for your ALEX homework, your recitation, and your exam. Now what we're going to do is we're going to take together 2 reactants, and we're going to look and say, which of these 2 reactants should be ionized and which one should be reduced. And we'll use this table to discern that. So let's go back and try this with a problem. So we have 5 problems here, and let's look at the first one. We have manganese solid reacting with gold 3 ions. So the question you ask is manganese more likely to be oxidized, or is gold likely to be oxidized? Let's go back to our activity table, and we'll notice that gold, Au, is at the very bottom. That's the least reactive metal on here. Therefore, it wants to exist in the metallic form. The reactant is manganese, and manganese is about 2/3 of the way up this list. Manganese should exist in its ionized state, or its +2 state. So let's look at this. Manganese does indeed react to form manganese 2 plus gold. Next up, let's look at iron 3 and cobalt. Which species is higher in the activity series, iron or cobalt? Iron is. And since iron is already ionized and it's higher in the activity series, nothing happens. The reactants stay as they are. There's no reaction. The third reaction we have is HCl plus iron. We don't see a metal on the left-hand side, but we see an acid, and that means we have a proton, and a hydrogen is part of the activity series. Let's go back up and look. Note that hydrogen is almost at the bottom. That's that blue box. It says H2, and that's H2, and that's hydrogen in the reduced form. In the oxidized form, hydrogen is H+, acid. So now what you see from this is any metal below hydrogen in the activity series doesn't react with acid. That would be copper, mercury, silver, and gold. Any metal above hydrogen will react with hydrochloric acid. So we go and look, and we see, sure enough, iron is above there in the activity series. Iron gets oxidized to iron chloride plus hydrogen gas. Next up, we have nickel and lead. And if you look at the activity series, you will see that lead is well done on the activity series. Therefore, lead goes to the metallic form, nickel gets oxidized. And finally, we have hydrochloric acid with copper. And as we know, copper is below hydrogen. Therefore, it does not react. It stays in the metallic form. That concludes Chapter 4. Next, we're going to move on to Chapter 5.